Hello, everyone.
Okay, let's start.
Yeah. Are you gonna? Yeah.
Yeah, I was going to introduce you. Hello, everyone. Sorry.
Sorry, I started. I stole your line. Yeah.
Sorry. Welcome to the fifth Solar Lecture Series of the year. Today we have Professor Philippa Browning from our very own Georgia Bank Observatory. Professor Philippa's main interest is about theories of solar fusion, and fusion theories. And as today we're about to hear a lecture about solar flares and space weather, let's give it for Professor Philippa Browning.
Right. Okay. So I'm going to talk to you about solar flares and space weather. I work in St George Bank Centre for Astrophysics, and for those of you that don't know me, I'm in the astrophysics group, which is across the way in the Alan Turing building. So I'm going to begin by just introducing the sun, which might be familiar to most of you, but just in case it's not. But my focus is going to be on solar flares, so I'm going to talk about what they are, how do they happen, and then move on to how the sun affects the Earth, and then the idea of what's space weather, which is in my title. And at that point, I'll also deal with another question, and we'll see in a moment sort of what this really means, but why is the solar corona so hot? And it turns out we maybe get a sort of answer to that sort of for free if we look at solar flares. And at the end, I'll just tell you very briefly about some sort of recent developments, sort of new missions and so on. And I'll aim to finish, in time for there to be a few questions as well, so I might just skip through things and try and finish, so there's time for questions at the end. So do save up your questions. So, watch out, I've made this lethal across here now, with, so I can face the same direction. So to begin with introducing the sun is we could say a fairly ordinary, smallish, middle-aged sort of star. And one of the key things is it generates energy in its core, where the temperature is about 16 million degrees, by nuclear fusion. So protons fuse into helium. But I'm going to move, as it were, swiftly up towards the surface, and we get to the visible surface, which is the photosphere. And that's where the light or photons that we sort of receive at Earth have come directly. They've travelled freely through space from the photosphere. So I say when you think of sunlight, that's where it's come from. And this is an image from a telescope called DKIST, which I might mention again briefly at the end, a very high resolution optical telescope. And you can see that there is a lot of structure there. There's this kind of honeycomb pattern, and it's sort of changing as well. And this is a sign of convection, where sort of hot material is rising and cool material is falling. And that's how the energy gets out through the outer layers of the sun. And this convection, this constant sort of stirring or motion, is quite important in terms of putting energy into the outer atmosphere, which is what I really want to focus on. So if we go further above the surface of the sun, above the photosphere, we get the corona. And really the rest of my talk is focused on the corona. And that's the bit that at Earth you would only see at a total solar eclipse. Anyone ever actually seen a total solar eclipse? Nobody? You have? Right, well, yeah. I've seen two, but one of them was a bit of a failure and the other was not that great. But you should see one if you can. But you'll have seen images like this. And here the moon has blocked out the light from the photosphere, and we're seeing the very faint emission from the outer atmosphere, the corona. So that's the stuff, outside the sort of surface of the sun. And even with this eclipse image, you can see there's actually a lot of structure there. It's not just a sort of, smooth white halo. There's lots of sort of rays and loops and filaments and so on. And two important things about the corona. The first thing is that the temperature of the corona is about 1 or 2 million degrees. Actually, I forgot, I think, to remind you, or to tell you, that the temperature of the photosphere is about 6,000 degrees. And the temperature of the corona is 1 or 2 million degrees. And you ought to find that surprising. You ought to go, hang on, how did that happen? Because you're moving away from, you know, where the energy comes from in the core of the sun, and it's actually getting hotter. And I say that is something we will return to later in the talk. But I say you ought to think that is, you know, quite mystifying, and in a sense it is. The second important thing about the corona is it's not actually just static. As you move away from the surface, it's streaming out into space, is what we call the solar wind. And by the time you get to the Earth's orbit, like where we are, it's whizzing past us at about 400 kilometres per second. And that also implicitly tells you another thing, and that is that we here on the Earth are basically living, if you like, within the corona, within the outer corona, within the solar wind. So it's not just like, hey, we're on Earth and we're sort of looking at the sun over there. It's part of our environment as well. And that's something, again, we'll return to later. However, if you want to see the corona, one might say, properly, the best way to do that, or the way to do it, is to have telescopes in space. And the reason is that because the corona is so hot, the peak of the emission is in X-rays, and X-rays don't penetrate the Earth's atmosphere, which is kind of good news for us from one point of view, because they would, you know, be very dangerous for us. But it is bad news if we want to look at the corona. So we have to build telescopes in space which look in other wavelengths like X-rays and extreme ultraviolet. And here's a couple of examples: Solar Dynamics Observatory and Hinode. And we'll see some other examples later. So if you do look at the sun from space, from the telescopes on Solar Dynamics Observatory, this is what you might see. And the three colours correspond to three different wavelengths, and hence to three different temperatures. So the blue is kind of the coolest, and the sort of reddy colour is the hottest. And you can see that the corona is very highly structured, and also it's constantly sort of changing in time. And if you look at that in close-up, now just looking in one wavelength, so essentially just looking at one temperature, you can see, you know, how that structure works. So in particular, you can see over here on the right, this bright regions with these kind of loops, and then some more, you know, loops and things coming in over the top left there, and so on. And also changing a lot in time as well, constantly sort of flickering and flashing. So what's going on? Well, the first thing is to understand that the corona is very hot. So it's made not of a normal gas, but of plasma. And plasma is what we call the fourth state of matter. So if you go from a solid to a liquid to a gas, but if you heat the gas up further, you will sort of tear the atoms apart, and you get a sea of positively charged ions or nuclei and negatively charged electrons. So if it's hydrogen, there'll be just protons and electrons, which are sort of moving about independently of each other. So it's no longer each electron has its own proton, as it were. They're just moving about freely. Now, one key thing about a plasma as compared with a gas is a plasma is a very good conductor of electricity because it consists of charged particles, and also because it consists of charged particles, it interacts very significantly with magnetic fields. And in fact, it turns out that the magnetic field of the sun and its interaction with plasma is really what's controlling everything that goes on in the solar corona. So what we're looking here is now a series of images from, again, Solar Dynamics Observatory. And we're going here, you're seeing the plasma in the corona, and then we're going to the magnetic field at the photosphere. White and black correspond to strong magnetic fields. Grey is kind of like zero. And you can think of white as being magnetic field coming towards you, black coming away from you. Or equivalently, you can think of like a bar magnet with a north pole and a south pole. And I hope you can see very clearly as you go from one to the other that there's a very strong connection between the magnetic field and the plasma in the corona. And in particular, we get these loops with lots of sort of hot, bright plasma where the magnetic field is strong. So the magnetic field is sort of trapping and structuring the plasma. So to look at the sun today, here is a magnetogram. This is a map of the magnetic field at the photosphere. Again, you can see a strong region of the sort of white and black there, strong magnetic fields sort of coming into the sun and out again. Another quite strong region there. And you can see some of those are associated with sunspots on the photosphere. And I'll come back to those in a moment. And I hope you can see, if you look across to the image on the left, there's a clear connection between what you're seeing down here and the plasma in the corona. And this is an image showing, again, the different temperatures, blue cooler, the yellowy colours, and the red being hotter, and also magnetic field lines. And you can see how the magnetic field lines are sort of emerging from these strong regions and trapping or confining the plasma. So I mentioned sunspots. I'll just say a little bit more about that. So we see them, as we've already seen, as black spots on the photosphere. They look black because they're cooler than their surroundings, a mere 4,000 degrees. And on the left, we've got some of the very earliest sunspot drawings. People always credit Galileo with discovering sunspots, which he kind of did. But this is Thomas Heriot, who was an English astronomer who independently discovered them at the same time. So the actual drawings there are Thomas Heriot's drawings of sunspots. And you can see how actually detailed they were and how well they correspond to our sort of modern images. But why a sunspot is important sort of for our purposes is they are in sort of a sign of a strong region of magnetic field sort of poking out through the surface. So we have a big bundle of strong magnetic field lines which poke out through the surface and then fan out, giving you this characteristic structure of a central umbra and the penumbra kind of radiating out. They generally, as it were, the magnetic field goes back in again, and actually you could see that if we go back to today's image, you can see there was a white and a black. So the field comes out of the sun and goes back in again. And that's quite characteristic. So sunspots are a sort of symptom of strong magnetic fields. And actually one of the interesting things about sunspots is if you count them sort of, day by day, week by week, year by year, there's a pattern. And generally, they form a sort of 11-year cycle. And we can see going back right at the beginning there to sort of about 1600, where we have Galileo and Heriot making the first observations. Interestingly, the sunspots kind of disappeared in the late 17th century. But that would be another talk to talk about that, so I'll just leave you to be intrigued by that. But generally, you can see this rising and falling cycle, and actually quite big cycles in recent years. And why this is perhaps particularly important for what I'm talking about now is the magnetic field that's sort of, indicated by sunspots affects the whole structure of the corona. So the corona changes over the solar cycle. And this is a series of images of the corona from an earlier satellite called SOHO. And you can see at sunspot minimum in 96, the corona was quite sort of faint and dim. The magnetic fields were quite weak. We get to solar maximum at about 2001, where you can see there's a lot of these sort of bright regions associated with lots of sunspots. And as you move through towards the end of the cycle, the sunspots decline and your corona goes back to being quite sort of faint and less active. And to give some context, this is a blow up of the most recent years of the sunspot cycle. And you can see where we are now, it looks like we're just coming to a peak. So we're at levels of quite high activity, lots of sunspots, lots of flares, and so on. So now let's come to the main subject, which is flares. So I'm going to go back in history a bit again, this time only as far back as 1859. And this guy, Carrington, had apparently his own observatory down in Surrey, Sussex, I always get them mixed up, and he was in his observatory looking at the sun and sort of drawing it, because that's what he had to do, and he noticed that there was suddenly the sort of a small region sort of within these sunspots kind of brightened, a very strong brightening. He'd never sort of seen anything like it before or heard of it, but he sort of noted it down in his drawing. And then over the next couple of days, there were reports of all sorts of things happening all around the world. So this ship, the Southern Cross, was sailing in the tropics and saw aurora, where sort of no aurora should normally be. And people were working in telegraph offices, sending, messages along cables. You can see these, elegantly dressed Victorian ladies kind of typing in their whatever sort of Morse code, I guess. And fires broke out in the telegraph offices, and one operator was knocked unconscious by an electric shock. Measurements of the magnetic field from across the globe, from Bombay to Kew, nearer home, showed these sudden spikes in the Earth's magnetic field. So the Earth's magnetic field had this kind of glitch. And Carrington speculated that what he'd seen on the sun was sort of causing all these various strange disturbances on the Earth. And so somehow the sun was affecting the Earth's magnetic field, inducing currents and so on. But he quite sensibly said, well, he can't be sure. He said, one swallow doesn't make a summer. It could have been a coincidence. Of course, it wasn't. We now know that what he did see was a particularly large solar flare that had these quite dramatic consequences at the Earth. So this is the first observations of a flare. So of course, what he didn't have was instruments in space or anything like that. So let's come now to our sort of modern understanding of flares. So flares are kind of explosions in the corona of the sun. They release about 3 times 10 to the 25 joules, or at least up to that, in a large flare over a few hours or minutes. And to put that into context, that's about 100,000 times the annual energy consumption of the Earth, of humans. So that is a lot. That's a big explosion. Okay, happening in a relatively short time. And you can see it in this movie on the right. You can just see this sort of huge burst of X-rays and extreme ultraviolet light. The whole thing just sort of lights up. And another, I particularly like this movie. This shows you a more sort of complex flare, a more high resolution. So you can see the flare going off sort of up there. What happens is the loops kind of brighten up, and then you can see a disturbance sort of spreading, the loops brightening up sort of one after the other. What you can also see, if you look carefully, you'll see something being sort of thrown out into space there. Did you see that in the bottom right-hand corner? And you can also see a disturbance kind of propagating away, something like a sort of seismic wave. So a lot going on, quite a complex event, but certainly a big release of energy. So what do we think's happening? Well, we're getting emissions of electromagnetic radiation in basically pretty well all wavelengths of the spectrum, from radio at one end to hard X-rays at the other. And this is resulting from the plasma being heated to temperatures over 10 million degrees. So remember, the corona was typically 1 million degrees. It's now going up to sort of 10 or 20 million. And we're accelerating sort of beams of charged particles up to sort of relativistic speeds, close to the speed of light. And it's this very hot plasma and these very fast-moving particles that are basically producing all this radiation, which is what we actually see. And what's causing it? Well, we think the only thing it can be, basically, is a release of stored magnetic energy. And, wait a minute. So if you take a rubber band, it turns out magnetic field lines have tension. And if you stretch a rubber band, you obviously build up energy. And if I were to keep stretching and stretching it, what would happen? It would snap. And basically in the same way, we build up energy in the magnetic field by stretching it or sort of twisting it, and then that free energy can be released, which gives us our flare. However, it turns out, and at least if you're a physics student, you'll know that there are no magnetic monopoles, so you can't actually just break a magnetic field line like I could my rubber band. So the field lines have to do something we call magnetic reconnection, in which they sort of break and instantaneously form a new connectivity. And that's illustrated in the little movie. You can see the two field lines sort of come in from the top and bottom, and at this X in the centre, they re-emerge connected in a different way. And that is restructuring the magnetic field and releasing stored magnetic energy, which in turn heats the plasma and can accelerate charged particles as well. So how this might happen in an actual flare is shown in the sort of cartoon on the right. So you see the field lines have been sort of stretched up, again a bit like my rubber band. I sort of stretch it and stretch it. And as they stretch, they kind of come together, and you can see that X there, and the arrows, that's where the reconnection happens. And that heats the plasma, accelerates the particles, and so on. Now in the flare I showed you earlier, we saw something being ejected into space. In a moment we'll see a much better image of that, but we can see it in this kind of cartoon. If you see the kind of twisted loop, you can see the thing at the top after the reconnection, that's being sort of catapulted into space. And again, I can show that with my trusty rubber band. So if I have a little piece of plasma here, and I stretch my magnetic field lines and then let them go, I can catapult some plasma into space. And that's exactly what often happens in a flare. And we get this coronal mass ejection. Except that movie's refusing to work. Never mind, we saw it with a piece of paper anyway, and you saw it in the flare I showed earlier. So that's one thing flares do. I've also mentioned they produce these very high energy particles, say with a sort of relativistic speeds. That's both electrons and protons, and they can do two things. They can either go out into space, and that we'll see is important later for space weather, or they can sort of crash into the surface of the sun. And we don't see the charged particles directly, but we see the radiation they emit. So when they crash into the surface, they emit hard X-rays, and the protons can even emit nuclear gamma rays. If they go out into space, or if they're trapped within the magnetic field lines, they can emit radio emission. So here is a space mission which we learned a lot about the hard X-rays and gamma rays from flares. So it was a hard X-ray and gamma ray sort of imaging telescope in space called RESI. Has been defunct for some years, but we learned a lot from that. And here are a couple of solar radio heliographs in Japan and France, which look at the radio emission from the sun, and especially from flares. And this little movie just shows you a sort of composite of Solar Dynamics Observatory in green, which is showing you the hot plasma, and effectively you can see the magnetic field kind of restructuring and reconnecting. And then the red and blue contours are the high energy electrons as observed by RESI. And you can see a strong correlation between the reconnection of the magnetic field and the formation of the high energy electrons. So in my title I promised to say something about space weather, so that's what I'm going to come on to now. So first I want to talk a bit about the elements of space weather. We've already mentioned coronal mass ejections, and this on a much larger scale is showing you a coronal mass ejection. So we have artificially blocked out the disk of the sun with a sort of artificial eclipse, and then you can see, I'll run it by again, a big sort of loop propagating out into space. And we think that's actually a big twisted magnetic flux rope which expands and expands and moves out into space. Now, this particular one is obviously sort of going sideways. So if you're sitting over there, you're kind of fine. But you can imagine, obviously, they'll come out in all directions. So from time to time, ones will come straight towards us or straight towards the Earth. And they can have an effect on the Earth and also any sort of satellites, that are orbiting the Earth. So for space weather, it's helpful to think of the Sun and the Earth as a system. This is an obviously not to scale picture, but on the one hand, you've got the Sun over there emitting coronal mass ejections, also radiation and high energy particles. And we are over here at the Earth, protected by our own magnetic field, but not fully protected, as we shall see. So the coronal mass ejection you can see in that particular picture looks like it's sort of heading towards the Earth. So solar flares actually produce three things which you could say are the elements of space weather. The first is X-rays, the radiation, and those can affect the Earth's atmosphere, particularly the ionosphere, and cause radio blackouts, among other things. These high energy particles may reach the Earth. They can certainly affect satellites, also other sort of technology. And these coronal mass ejections, if they hit the Earth, can disrupt the Earth's magnetic field, which also has sort of consequences. So here is an example. It's harder to see, but this was a coronal mass ejection which was coming straight towards the spacecraft. And it actually hit the spacecraft, which is why everything goes kind of dotty, because of the impact on the spacecraft. And if you think back to the Carrington event that I showed you a little while ago, you can begin to see, what he was seeing. So, for example, that disruption to the Earth's magnetic field, that was caused by the coronal mass ejection impacting on the Earth. So this is a sort of artist's impression. Oh, no, it's not. I don't know what's happened to my movies. This one isn't working either. Never mind. This would have shown you what happens when a coronal mass ejection crashes into the Earth's magnetic field. But what it does do, you imagine the Earth's magnetic field is kind of flexible. So when a coronal mass ejection hits it, the Earth's magnetic field is, if you like, shaken or disturbed, and that in turn can even cause magnetic reconnections within the Earth's magnetic field and disruptions of the Earth's magnetic field. And also, you will notice, if you look at the Earth's magnetic field, you can see it isn't a perfect barrier. And so if you look particularly at the poles, you can see there are cusps where there's a kind of direct connection from the solar wind down to the Earth's surface. So energetic particles from a coronal mass ejection, for example, can sort of leak in, and they will particularly impact on the poles of the Earth. And when they do that, what you see is an aurora. So here, obviously in the northern hemisphere, is the aurora borealis. There's an image of the aurora from space. You can see it forms a kind of oval around the poles. And this is a schematic. So you've got, again, now you can see the Earth's magnetic field. You can see more clearly the sort of cusps where particles can leak in and get down to the polar regions. And also we can create energetic particles within the magnetosphere itself if it's been disrupted by a coronal mass ejection sort of slamming into it. Now, as I mentioned, this did have some observable effects on the Earth when Carrington observed it, but obviously a lot has happened since Carrington time, and in particular we now have satellites, we have electrical power, we have space missions, and all these things are significantly affected, or can be significantly affected, by solar storms. So the first thing is these high energy particles could be very hazardous, if not fatal, if you were an astronaut in space. So you might want to think twice about going to Mars until someone's found a way of dealing with that. And even if you take a sort of transatlantic flight, going over the polar regions, well, that can normally give you a significant radiation dose. It's like having a chest x-ray, but if there's a solar storm, then even planes will be grounded. But here on the left-hand side, you see a transformer from a power station, and that was knocked out by the induced currents from a solar storm, and there was a power blackout, and that can happen from time to time. And also particularly satellites, and of course we're all very reliant on satellites in a way that we weren't, even sort of 20, 30 years ago. None of us could live without our mobile phones or whatever, and GPS and satellites can be significantly either damaged or just knocked out by these kind of effects. So in 2011, solar storms were added to the UK National Risk Register, and the UK Met Office for the last 10 years has been operating a space weather forecasting service. And this image is from the Met Office sort of brochure, and you can see some of the effects. There's the sun up there. You can see effects on satellites, effects on the upper atmosphere, effects on planes, effects on power cables and generation, effects on underwater cables for communication and power, and so on. So a complex web of technological effects, and certainly considerable economic impact. And if that wasn't enough to worry about, we can also mention super flares. So a few years ago, Kepler, which was a spacecraft predominantly looking at exoplanets, but obviously also had to observe stars, discovered that there were flares about 1 million times more powerful than the largest solar flare on some solar type stars, sun-like stars. So apparently these stars have really massive flares, and of course that leads to the question, well, could this happen on the sun? Obviously it won't happen very often, but occasionally might we get one of these very big flares? If so, what would it happen? What would its consequences be? People have also been looking back in the past, evidence from sort of tree rings and ice cores and the like, of when there were almost certainly now big flares at times in the past. And it appears in 775 and 993 AD there were particularly large events. And again, well, what if one of those happened now? They didn't have satellites then, they didn't have power systems, so they didn't mind too much, but it would affect us much more. And even if we get another big flare as big as Carrington observed, which we almost certainly will do, and if it's sort of coming in the right direction and certain things, what will the effects of that be on our technology? So lots of things to think about there. But I now want to come back to a question that I sort of mentioned at the beginning, this issue about the corona being so hot. So it was discovered back in 1939 that the temperature in the corona is over 1 million degrees. And ever since then, it's been a sort of major unsolved problem in astrophysics to explain that. So what we do now think is it's almost certainly due to the magnetic field. That should be no sort of surprise by now. And basically we are shuffling the foot points of the coronal magnetic field, building up energy, and then converting that somehow into heat. So there are basically two competing theories. Well, of course, it may well be that the truth is some combination of the two, or lies somewhere in the middle. So one is what we call nanoflares, and the idea that in a flare you release magnetic energy and heat the corona. But the sort of flares I've been talking about so far, the big flares, although they do sort of put energy into the corona, they don't happen very often, so they don't have much effect on the overall temperature of the corona. But there could be lots of little flares sort of going on all the time, and they will be much more frequent, and the combined effect of those flares, the many nanoflares, could heat the corona. The alternative is waves, where you imagine shaking the magnetic field lines and generating waves which propagate into the corona. So nanoflares is basically just dissipation of electric currents through reconnection. Waves, well, you all know that waves carry energy. So sticking more on the nanoflare side, the idea is you could either twist or tangle the coronal magnetic field lines, and that will create lots of sites of magnetic reconnection. So everywhere where different sort of magnetic field lines, which are sort of discontinuous, interface each other, you'll get reconnection. And it may well be that the coronal magnetic field looks a bit like this, minus the cat. So this very tangled, twisted, complex field means reconnection is sort of going on everywhere, or all over the place. And so still on a cat theme, I just want to mention very briefly what sort of I do and my group here at Manchester. So as shown by the picture, most of what I do is sort of computer simulations and modelling. So we're interested in, how is the corona heated by nanoflares? How do we accelerate these high energy particles? And more generally, just how does reconnection work? And here's one example of one of our simulations where we twist up a magnetic field line till this bundle of twisted magnetic field lines goes unstable and reconnects. And you can see you build up strong currents and hence heat the plasma. And the yellow is showing you like locations of hot plasma which are emitting X-rays in the simulation. And the key thing there is you would see the yellow stuff, the radiation. You don't see the magnetic field lines. We can simulate them, but they are, not directly visible. We've also been working on what we call avalanches, and the idea of an avalanche is, one bit of snow falls, brings down more snow. But here we have a kind of magnetic avalanche where one bundle of magnetic field lines goes unstable. That then disturbs a neighbouring bunch of magnetic field lines, and you get a kind of chain reaction or avalanche in which the whole field kind of disrupts and reconnects and again heats up. And we've also been doing more sort of data-driven models in which we take measurements of the magnetic field at the solar surface and then simulate the evolution of the magnetic field and watch how the magnetic field evolves during a flare. And in this case, we also calculate how particles have accelerated. So we find where there are regions of strong electric fields which accelerate the particles. And in this case, we are visualizing where those high energy electrons impact on the solar surface. And in turn, we can then match that to the hard X-rays and so on that we see. So very briefly, I'm just going to mention some of the recent developments in observational solar physics. I already showed you at the beginning some images from DKIST, which is a very high resolution telescope in Hawaii, looking at magnetic fields and velocities at the photosphere. But then two very exciting missions, which we could say are actually visiting the Sun. Parker Solar Probe, launched in 2018, a NASA mission, has been sort of spiralling closer and closer to the Sun. And in its final 3 orbits, it will get within 8.5 solar radii of the surface. So this is literally sort of flying inside the inner corona and sending us back direct measurements of what's going on there. And I just put up this picture because this was Parker Solar Probe before it was launched, obviously, but just, it was almost ready to go. And the reason for this particular picture, if you look at the guy at the front there, with the, well, they've all got silly hats on, but the one just, immediately in the front looking towards the telescope, that is Parker, that it was named after. Quite unusual to name a mission after a living astronomer. Unfortunately, he has subsequently died. He was about 90 something. I think he was about 90 when this picture was taken. But he was the guy who discovered the solar wind, effectively. He predicted it from theory before it was measured. He more or less developed the theory of magnetic reconnection and also the theory of nanoflares. So it's nice that he got this mission named after him. And then Solar Orbiter is the European mission launched a couple of years later, also going quite close to the sun, but not quite as close. But also that's got two unique things. First of all, it goes out of the ecliptic plane, so it's looking down on the poles of the sun, and also it has a much better combination of instrumentation. So it's both measuring things in situ, in other words, where it is, and then looking at the sun remotely, and then it's able to sort of put those things together. So you can say, look, we see this happening at the sun, and then here we are, we then measure the effects as it sort of comes past us. So the combination of those two missions is immensely powerful. I think that's Solar Orbiter being launched. I won't go into this, but this is just a sort of compendium of some of the early results from the first closest approach of Solar Orbiter, measurements of the detailed measurements of the magnetic field. In particular, it discovered these things called campfires. It doesn't look very good in this picture, I'm afraid, but if you see these little sort of white blobs, these are little tiny brightenings. So there's something like the nanoflares, like lots of little mini heating events going on, which Solar Orbiter was able to see for the first time. So I think I'll stop there to allow a little bit of time for questions. And basically the bottom line is we have learned a lot, but there's still plenty we need to learn. We need new space missions, more simulation, higher resolution ground-based telescopes, and hopefully we'll begin to understand the sun a bit better. So, thank you.
How often does the solar flares seriously impact Earth? You said about the flights.
Yeah, I think the flights would be a really big. Well, of course, how often does a flare happen?